But
Yeah. All right.
um,
That's exciting.
it is. I'm excited. So, if I may, before I fully jump in, could I ask you to introduce yourself?
Yeah, absolutely. So, my name's Daniel Casey. I'm a physicist here at Livermore Laboratory, and I work specifically at the National Ignition Facility on fusion experiments. So, my day-to-day job is exactly this kind of stuff, trying to make sure the experiments are conducted at the laser, that we're learning from them, and trying to understand, what's happening.
That's excellent. And what field would you have gone into in order to get to that point?
Yeah, so I had kind of a funny path myself into this field. So I started off in nuclear engineering, studying, reactors and stuff like that. And then I went in my PhD work, study plasma physics.
Okay, very cool. Excellent. Do I remember seeing that you went through MIT?
Yes, that's right. Yeah,
Excellent.
so that's where I got my PhD from MIT, and then my undergrad at the University of New Mexico.
Very cool. Okay, then I'll jump in with my first official question. I wrote out a little bit. I'll
Yeah.
read it through. Um,
Okay.
I understand the basics of National Leadership Facility. Truly, I feel like it was first 8 to 10 years ago that I'm putting forth the animation before my students, where you have the 192 lasers. And I don't know if you saw that old animation. It's not high quality. Looks like it was made in Macromedia Flash, and it's showing all the path of the lasers as they go through. They get amplified, and they end up get focused on one small point where you have this little half the diameter of a BB size piece of fuel, and then there's nuclear fusion. And that's honestly the point where I start to lose things a little bit because after that, somehow the energy is captured. You have this incredible megajoules worth of energy later on. But my question early on before I get lost in that piece is it goes through this path. It's a long path that it's going through in this facility, these 192 lasers. Could you tell us a little bit about that journey that it goes through and how powerful each laser starts at compared to what it ends at?
Yeah, sure, sure. So it sounds like if you've watched that video, you probably know about as much about the laser as I do. So, um, but what I can tell you is it starts off pretty humbly. So it's on a breadboard, like a little thing that you can see with your eye that looks a lot like a homemade laser pointer. It's a really small single point laser that the entire system is fed off of, and it's on the order of like a nanojoule. So
Hmm.
it's not a ton of energy, and it what makes it special is that it's very precise and very short in its time scale. So it can construct these very precise pulses that then get fed off. So then this little tiny laser splits into two pieces and it goes into two different rooms that are like the sizes of warehouses. So there's two huge amplifier bays that we call laser bays, and they're separate. And from there, the two pieces split into 48 pieces total. And that
Hmm.
goes through the amplifier back and forth. And at the end, it gains, it gets into the megajoules of energy. So it starts
Hmm.
off in nanojoules, goes to megajoules. So huge amounts of amplification. And the beam path is, bounce, the laser goes back and forth through these amplifiers. It's like a mile of
Wow.
travel, even though, I mean, the facility's big, but it's only, the size of like a warehouse, but they're bouncing back and forth. The entire process itself is amplified over the scale of like a mile going back and
Okay.
forth, which is kind of cool if you think about it, because when it focuses down on that target, like you were saying, the target itself is, half a BB size, right? So it's like a millimeter scale. And the precision at which it's got to hit the actual target is microns. I mean, it's so if you think about, a laser that is the size of a warehouse that's having to go back and forth over the scale of a mile, has to hit a target on the order of and hit it in the right place on the order of a micron. It's just, I mean, it's really kind of hard to capture that kind of differences of scale,
Yeah.
right?
I hadn't thought that much about that aspect of it because we talked about, I'm going to flirt with disaster for a second here. Okay, did I successfully make it around? I grabbed my James Webb Space Telescope model here,
Uh-huh.
And I hadn't thought much about the similarities, about how they spent months and months trying to micro adjust their tiny mirrors to get it focused to an exact point. You probably have almost like a greater level of necessary precision to try to, because if your mirrors are off by, because it is mirrors, right?
There's mirrors, there's optics, there's amplifiers, all sorts of components that, I was only half joking when I said that video taught me everything I know about the laser. So I'm not going to be able to explain everything, but uh, yeah, I mean,
Okay,
it's a lot of components.
cool.
Um, yeah.
Do you have, I only know, and I trust that what you said is more what you need, but I only know lasers as far as talking about them on the order of watts, milliwatts, things like that. You're referring to on the order of joules, probably because it's a compact burst of energy going through. So watts is joules per second, and you're talking about how much are you actually sending through in kind of each packet, almost each burst of energy. Do you guys ever think about it on a watt level or not really?
Yeah. So I think you're exactly right. The reason we think of joules is because it's such a short burst, right? And the burst is on the laser time scale on the order of nanoseconds to 10
Mm,
nanoseconds. So it's very, very, very short. That's, blink your eye and that's, I don't know, billion times longer or something like that,
right.
right? And so the time scales that we're talking about are very short. And so just a few joules, or in the case of this laser, 2 megajoules over that time scale is hundreds of megawatts. So, that's a lot of power, but it's for
Right.
a very short amount of time.
Excellent. Do
So
you
the laser
know?
itself, just to finish, I guess, answering
Yeah,
your question, it peaks out at about 500 uh, terawatts. Sorry, I think I said megawatts. It's terawatts, 500 terawatts in UV light at the target. That's the peak power.
that's no household laser.
Yeah,
That's
yeah,
the little one that we might play with our cat with is around 5 milliwatts. Can I do it in my head, order of magnitude conversion to get from that, not off the top of my head, but to get from what you or I might have there to just play around with a cat of 5 milliwatts? I know I have a laser in my room that's a 1 watt laser, and a 1 watt, they warn you, can burn hair or skin. An indirect reflection can cause temporary eye or permanent eye damage before you can blink, all these other things. And that's 1 watt. You're saying 500 terawatts.
yeah, that's right. It's so much power that it'll ionize the air and it won't even go through it. It just makes a plasma.
So is it a vacuum that it goes through
Yeah,
effectively? Cool,
yeah,
cool.
yeah. I
I
mean,
love
the
it.
the final part is a vacuum. Earlier, it's like neon gas, I think, or some kind of noble gas that it goes through.
And does it start or end at 500 terawatts?
That's where it ends.
Okay,
So on target, the the laser is focusing down, and the power that is delivered is on the order of 5 terawatts.
amazing, brilliant.
500 terawatts. I keep saying it wrong.
No
500
problem.
terawatts. Yeah.
That's awesome. Very, very cool. I love it. Okay, I'll go right on to my second question. This is excellent. I wrote here, can you elaborate more on how the energy of the explosion is actually harnessed and turned into something usable? Many other energy generation facilities often rely on turning water into steam, driving some sort of mechanical gear process, but you're not talking about that really. There's something else going on here with this. So could you tell us a little bit more about that piece that I'm honestly a little confused about? I understand it bounces, it amplifies, you hit that BB, then what?
Yeah, great question. So what happens in the experiment itself is that you're heating things and compressing things so that they're hotter than the core of the sun, denser and higher pressure than the core of the sun, and that enables the fusion reactions to happen. And they when they occur, they produce energy. And the energy in the fusion reaction that we're using, which is deuterium and tritium, combining together to make helium and a neutron, the energy is released in that helium nucleus and the neutron.
Okay.
So in the experiment itself, the helium nucleus or alpha particle is what um, feeds back on the system. So it heats itself, and that's what enables it to burn like a a log of wood or something,
Hmm.
because of the helium nucleus or alpha particle redepositing its energy in the plasma. The neutron just flies out. And the neutron is what carries most of the energy. And so it's carrying most of the energy away from the system. So in our experiments, what we do is we put a bunch of concrete and basically just try to stop the neutrons from getting, out and causing problems or radiation safety hazards. And we study them. We don't really do anything useful with
Hmm.
them in terms of making power. We're really, it's a scientific experiment, and we're collecting them only for the purposes of trying to understand what happened in the experiment. So
Huh.
in fusion power systems where people are thinking about, well, what are we going to do? How are we going to harness this power and use it to make energy? It's really back to what you said. The idea is to take those neutrons, heat some water and
Hmm.
boil it and send it through a turbine, or maybe heat a gas. They have these, they're imagining these big systems where they put blankets basically around the chamber, and those blankets capture the neutrons, they get hot, and you use that to boil water.
Amazing. That's fascinating. I wouldn't have guessed. I was sitting there trying to figure it out, but it is still fancy steam engine almost. Fancy
It
trying to
is,
get to boil
yeah.
water. And I
There's
that's
there's
excellent.
there's some there's some other concepts out there too that are honestly probably even more difficult than what we've done here. Like there's a reaction, instead of deuterium tritium, you can use um, a proton and a boron, p boron reaction, which instead of making a neutron just makes charged particles. And people have imagined, well, if you have only charged particles, maybe you could use them to do work against an electric or a magnetic field or something
Hmm.
and do some kind of direct energy capture. But the challenge is that reaction is much, much harder to get to go, like to burn, than the one we're trying now and really working very hard with. So, that's a cool idea that we should keep, in our back pocket. But in the end, our most promising concepts are really going to probably just be boiling water again.
Excellent. So you said that BB half BB pellet, and I should have known this. It is deuterium and what's
Tritium.
tritium. So those
Yeah,
together are making up the BB half size of BB, the fuel, and that's
that's
just
right.
getting burned. And
Mhm.
you mentioned that you're kind of detecting, just being aware of the neutron that's shooting off. Are part of your detectors bearing any similarities to detectors around like a Large Hadron Collider particle accelerator? Because they're watching what happens when a particle goes shooting off in some way there. You're watching at a specific moment when a particle is shooting off. Are there any similarities between your detectors and something that they might use?
Yeah, there is. That's a great question. The, one system, looks a lot like one of those particle physics systems in that it takes the neutron, converts charged particles from it. So it has a foil where the neutron interacts with the foil, and those charged particles go through a magnet, and then our momentum dispersed through the magnetic field. And that's, you know, exactly the kind of detector system you're going to find at a collider system like that,
Yeah.
right? We also have time of flight systems. So you have, since everything comes out in a burst, you can just put a scintillator that records when the neutrons interact with it some distance away, and it tells you how fast they were going when they hit it, because everything
Huh.
came out essentially at once. And you've got this thing, this detector that's pretty far away. So when you get the signal, it tells you the energy of the neutrons that came out.
Cool. Very cool. Thank you. I'm learning a lot. This is great. I'll go right on to my third question here. I wrote, I have a cautious optimism regarding this breakthrough. I've told my students that it has incredible potential to transform the energy world. I saw Neil deGrasse Tyson talking about his optimism for what you guys are going to do with that. But I also understand that this sounds very far from being ready for mass use or application. Right now, we're observing, we're talking about, we're speculating. Given the journey that has already occurred in the last 13 or so years at the National Ignition Facility, can you comment on what's next? What next steps need to start to happen to scale this into something that could be eventually a new power plant or something?
Another great question. I think cautious optimism is a really reasonable way to look at this. So I'm just incredibly excited because we have been working on this for 60 years. I mean, seriously, just decade on decade, one generation of scientists after another
Mm.
to get to this point. So we have really, you know, you know, sort of crossed a new threshold in our ability to harness fusion energy controlled in the laboratory. But the road ahead is also going to be very difficult. And the analogy I like to think of is like the Wright brothers plane flight, right? So they demonstrated plane flight with this thing that really was not particularly practical, right? But it took decades before people were able to take what, you know, they saw in that concept and start making passenger aircraft that go between, you know, San Francisco and LA. And that's kind of what we're looking at here, right? Like we have demonstrated that this is possible, but the path ahead is going to be decades, most likely, of really difficult engineering and physics challenges. And so just to sort of lay it all out there, so we made 3 megajoules of energy in the experiment last December that has really, for the first time, shown that we can produce more energy than we put onto the target. We put 2 megajoules of laser energy onto that target. So that's a gain of about 1.5. But the laser itself was not built to make a lot of energy. It's not an efficient laser. So it drew off the grid 300 megajoules. So if
Mm.
you look at this system and say, okay, well, how much energy did you make based on how much you drew off the grid? We actually lost a fair amount of energy. And it's because this laser is just not built to be efficient. So we need to make more efficient lasers
Mm.
than the one that has been designed here. And we have ideas for how to do that. Uh, so that's one thing. The laser itself needs to fire very rapidly. So in order to make this on the scale of power that's required for a city or something, you need to do an experiment like we've done once. You need to do it several times a second.
Mm.
So I mean, you have to really scale things up, and so it takes a particular type of laser technology that can fire that rapidly. And you know, the complexity of tracking a target and shooting it and shooting it and shooting it versus, you know, what we've done now is load it into the chamber very carefully and, you know, make sure everything's configured right, and then after a lot of time and effort firing once, we have to do it multiple times per second. So that's going to be a big challenge. And then to your question earlier, we have to capture the energy and harness it, right? So you've got to build a blanket system, like we were talking about earlier, to capture those neutrons. The fuel that we're using is deuterium and tritium. Deuterium is found in ocean water, so there's almost an infinite abundance of deuterium on Earth, enough to power, you know, the human race for as long as I can imagine. But tritium is not a natural isotope of hydrogen, and so it needs to be made. And so
Mm.
they have designed systems in the blanket to breed the tritium that's required for the reactor by putting lithium in the blanket. So that's another thing that we'd have to do, is we'd actually have to make some of the fuel in the reactor.
Mm.
Um, and so that gives you sort of a sense of some of the challenges that are ahead. They're significant, but you know, this is the moment where you can look back and say, you know, we flew the plane, right? It
Yeah.
got off the ground. It didn't go very far, but it got off the ground. So now that is, you know, for me personally, and I hope for a lot of people, the motivating factor to tackle these really hard problems ahead.
That's wonderful. I'm going to give you an honest piece here. If you were talking, I've been teaching for this is my 16th year teaching. When I was first mentioning this, maybe 10 years ago, maybe 12, somewhere talking about some stuff with what NIF was doing. Um, Part of for the first couple years I was aware of it, I almost would think of it in the idea of, well, America, we got the biggest laser. Because there wasn't something we'd look at and be like, but they're doing this with it. It felt to me at that point in time like we definitely have the biggest laser. No country has a bigger laser than we do. We got the biggest laser. And now we're reaping the benefits. Now it's like yeah, we have it, but here's what we can do with it. And now we've proven almost that there's a net gain, there's a potential. We got to work now. It's like you said, it's that founding moment. But I would no longer refer to it in that fashion because it's not just the biggest laser, it's the biggest laser, but here's what we're able to actually do with it in a productive manner, which is wonderful, which is awesome. Very cool. And changing my format for how I'll deal with it. I appreciate it. My next question mentions a book, and I happen to see that book sitting right there. I'm just going to grab it so I can point at it while I go through. Should have had it right there on screen ready, but out of curiosity, since it's the start of my next one here, were you previously? I imagine there's a fair chance, given your field, given your background. If I said Randall Munroe or what if, were you familiar with XKCD, him, any of that stuff?
So, it's funny, I have not read this book, but
Okay.
it was just a couple of months ago. I was having lunch with a couple of physicist friends of mine at a big plasma physics conference, and this book came up. And they were saying it was a really interesting book, and had recommended it. And one of the guys I was having lunch with told me he actually um, wrote a letter to the author correcting some story about throwing a baseball the
Yeah.
speed of light or something. So I haven't read it. I'm sorry, I don't have a lot to say about it, but I've heard that it's good, and it's on my list. I'd like to read it.
No problem at all. As somebody in the science field, this guy Randall Munroe is known as being he's got a computer science and physics background and has, I think, honestly, over the past, I want to say 15 plus years, maybe closer to 20, he's made his full living off of web comics and that, but he's very well researched on it. You'd appreciate part of that. And specifically here, it's one of the, I mean, I don't think the average person on the street knows National Ignition Facility or knows that much about it. I could be wrong. Maybe in your region they know more about it than they do in little Kennett Square, Pennsylvania. But I find myself educating me a bit more on that. But to this guy, it's like, well, of course, if we want to talk a big laser, let's talk National Ignition Facility and use them as a reference. In the one there, they look at the question that somebody had put forth for him was, if every person on Earth pointed a laser pointer at the moon at the same time, would it change color? And the half-second answer is no. There's nowhere near the energy. But our lasers are 5 milliwatts. Yours is 500 terawatts. And he was scaling up in a region. Did you happen to look at what he had for that? I wasn't
I
sure if you flipped
haven't
through.
seen it, no, but I want to.
I'll have to make sure you get the link for it because he ends up
Okay.
scaling to the level of, hold on, I think I can even do a real fast share screen for this. Let's do this. Let me put this in a separate tab here, share screen for that, and give you the reference for this because there's another piece with this. So if I hit share screen on this one, perfect, coming through now. We good?
I see it. Yep.
Okay, so there's your question. If every person on Earth aimed a laser pointer at the moon at the same time, would it change color? And nothing happens is the short form of it. And he even uses 5 milliwatts as a starting point for it. But then he starts to scale up on lasers and move past the more power piece to saying you can get a $300 laser, a 1 watt laser, similar to what we might have here. Still, there's no net result. That's nowhere
Dang.
near enough power. Scale up from that and say past that. Apparently, Coast Guard helicopters have a searchlight that's 50,000 lumens, and give a whole bunch of those to everybody, still nothing. And then ends up getting to IMAX projectors, no effect. Luxor in Las Vegas, a bunch of those, no effect. And the last step is give everybody, where is it down here? Where's National Ignition Facility? Megawatt lasers from that. I think you guys end up being the last step. There we go. 500 terawatt NIF lasers. So get a whole bunch of facilities, and the net effect is you destroy the moon. So if anybody had ever thought about what would happen if we had a huge fleet of lasers, apparently this guy did the math to say you destroy the moon with a whole bunch of National Ignition Facility lasers. But so my actual question was going to be, are people in your facility roughly familiar? And I guess some are. So some of the people you've encountered are familiar with this guy's work.
I've
But
heard about it. I heard it was good, and now I know I've got to read it. So I'll
if you've
go
got some
get
of the
it.
physics background, you'll just appreciate and chuckle at part of how he answers some things often. But I'll go right on to my last official one before I get to my surgeon question. I wrote, I've been aware of the National Ignition Facility for many years, referring to it as the world's largest laser, as I said, but I didn't know Lawrence Livermore. So I'd heard of NIF, but I didn't know this is all part of Lawrence Livermore National Laboratory. I'm sure there's so many things I don't know that are exciting at Lawrence Livermore. Your focus is NIF, but if you could just what are the other things that other fields, other things of interest that are going on? I heard somebody, I think was in a recent news report, saying that people joke around that, well, Lawrence Livermore LLL could be lasers, 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 because you're really focused on lasers. But besides NIF, what are the other cool things going on at at Lawrence Livermore National Laboratory?
Yeah. Oh, wow. There's so many things. I mean, so Lawrence Livermore National Laboratory is often joked lasers, lasers, nothing but lasers. Yeah. So
Hmm.
that's an absolutely common joke that's told around here because we've had a laser program for a long time, and it's basically grown up into what the NIF is doing. But there's some other laser work that's going on too in national defense and other areas that study what can you do with lasers, right? You can do a lot of interesting things. But Livermore itself is a big, primarily physics lab to study, national security related physics questions. So it has a lot to do with nuclear weapons and
Hmm.
studying how do we keep the existing stockpile safe and secure and without doing nuclear tests. So that's one of its primary missions. There's a global security area that looks at, what are other countries doing and how can science help.
Hmm.
And there's a huge computer industry here building up here at the laboratory, and there has been for a long time since the beginning of the computer. So I can never quite keep track, but we usually have one of the nearly fastest computers on Earth, like on the order of the first or the second or the third fastest. And then somebody will build a faster computer, and then well, we're going to build this computer now. And so computation is huge here, computer
Wow.
technology. And then what can you do with these computers in medicine, in nuclear weapons research, and then also in fusion research. We use huge computers to model these experiments and try to predict them, and try to learn, well, how do we make models smarter? Can we use artificial intelligence? Stuff like that. But it's a big lab, a lot going on: nuclear physics, chemistry, biology. Those are just some of the things I can think of off the top of my head.
That's awesome. Thank you. I feel like I have a better understanding. And you guys have one of the fastest computers. I wouldn't have guessed that. And I'm sorry if I say little NIF and little Lawrence Livermore compared to some of the mega labs that a lot of people are more famous in some ways. But that's saying that, like, I would think when I'm thinking of biggest laboratories, I would think of something like LHC, Large Hadron Collider, as being up there. But
Mhm.
what you're effectively saying is there's plenty of times where you have a better, beefier computer at your disposal than they would, which is pretty cool. That's awesome that you guys have that. Especially considering this is, I mean, National Ignition Facility. It's U.S. It's not some major. I'm sure you have other countries that you'll collaborate with and work with, and scientists across the world. But this is LHC is this conglomeration of so many countries and scientists and groups, and you are this is U.S. based in its entirety, which is impressive. Um,
Yeah, that's right.
I'll get to my surgeon question here. So
Yeah.
this guy, I had such a great impression. Wonderful chat with him yesterday. He wants me to make a Spotify playlist that's going to play in the operating room throughout the procedure for him. It's a great time, but he was totally wanting to get in on what's going on here, and he said that, and I'll just go ahead and give you the best of my reproduction of this. He said that while it won't be said that this breakthrough allows for easier testing of nuclear weapons, and I told him I don't think it's similar material. I hadn't heard anything about that. And he said, well, they wouldn't tell you about it. it's classified that they're, but the true breakthrough, he said the true breakthrough is not in energy. The true breakthrough is in being able to contain explosions and better test nuclear weapons in a way. And I said, I'll talk to the guy. I'll ask him, but I don't think the structure is the same. I know that's not posed in the perfect way of question, but have you heard similar people being like, "Oh, you're just testing bombs in a controlled way there"?
Well, it's quite a bit different. And I think the essence of the question, that as I can gather it, is, are we using these kinds of experiments to study weapons? And there's an element of truth to that. I mean, this is a nuclear weapons lab, and we do not do nuclear tests in the United States anymore. Which is almost certainly a good thing, right?
Yeah.
And we want to understand the weapon systems that we do have, make sure that as they age, they don't start to break or behave in some different way that we don't want to be surprised about. And so you can, uh, learn things in an environment like this that you can't do anywhere else other than in a nuclear test. I mean, imagine that the power that we've produced in these experiments is greater than all of the sunlight cast on to the earth. It's just for a brief moment, but that's an incredible amount of power.
Sorry about that. End of
Yeah,
the
no
day school
worries.
bell, but you're good.
Okay. Yeah. So, I mean, it creates conditions and power that really can't be reproduced anywhere else on Earth. And so you can, try to use these things to answer questions that are lingering from uh, um, the weapons program.
Very cool. And one last piece with this, if I can. I just had my students truly today, tomorrow, finishing up a small project looking at radioactive disasters. And we're thinking about energy, and I'm having them look at, of course, the big ones like Chernobyl and Fukushima and Three Mile Island, littler ones like wind scale fire in the UK and Kishtim out in USSR, the 50s. And it's more publicized and more aware of what can go wrong with a nuclear reactor on that side of things.
Mhm.
Um, if I know you aren't talking about really producing energy yet, you're getting there. I mean, there was a net gain kind of, but if we're trying to talk similarly, I mean, we have an awareness of what can go wrong. My students have been looking into what can go wrong with a nuclear reactor, but the fusion that we're now talking about, if we were to play a game like what is the worst that could go wrong on that level, there's not a nuclear waste, correct? There's
That's correct. Let me caveat that in a
yeah,
sense, because you're producing a lot of neutrons, and the neutrons are flying out, and the neutrons are making things radioactive in the facility. So the facility itself becomes radioactive, but it's controlled and contained. So it's like you're talking about, like, isotopes in the concrete are becoming radioactive that then can be, you just wait and they decay away. Rather than producing a waste that has to be taken away, it's the facility itself now becomes a radiation source, but that's not easy to release, right?
right.
It's contained in the facility.
Interesting.
Um, so that's one of the big promises of fusion energy itself, is that you don't produce radioactive waste, with that one caveat that the structural materials themselves do become radioactive. And the accident scenarios are not uncontrolled fusion reactions. Like in a fission reactor, you've got a lot of fissile material, or fissionable material sitting there, and if something goes wrong, it's a lot of fuel for a nuclear reactor to go out of control, right? In a fusion reactor, you don't have that much fuel in the system at any one time, so that if somehow it were to burn out of control, it would just burn itself out, burn up all the fuel. So you don't have that same uncontrolled reaction scenario that you might have in a fission reactor. Um, One thing that you might be concerned about is that there is tritium tritium is a radioactive material, and so you want to make sure that you don't somehow lose control of the tritium inventory that you're making. But that's just one of those things that you've got to work on.
That's awesome. Thank you. I feel like that's a wonderful way to think about this in comparison, because all that we've learned through, I mean, this is almost an extension of the nuclear world, just going from fission to fusion, but yet the overlap of what occurs in a fission reactor, like we've been talking about with these disasters, compared to what you do, it's almost no overlap for what is actually occurring. People think of them as both in the realm of nuclear energy, but the overlap is, if I were to do my Venn diagram, there's not much sitting in the middle for that piece of it there as far as the risks, what's going on with it, and it's a good distinction to make. But thank you. This has been a treat. I feel like I've gained so much from this, and I'm very much looking forward to being able to share this with my students.
Yeah, thanks a lot. It's a pleasure talking with you, and I hope your students enjoy and learn something and go off and solve hard problems. I mean, physics is fun, at least for me. And so I hope other people feel that way and build their careers doing physics, because every day it's just hard problems and it's exciting.
That's brilliant. Thank you so much. Again, I really do appreciate it. And I wish you luck as you're figuring out where to take this from here.
Yeah, thanks a lot. Good luck with your surgery, and
Thank you.
hope all goes well.
Thanks. Have a good one over there. Thanks.
Bye.
Bye.